Welcome, everyone. Uh, I am joined with John Lancaster. John is a MCE member, and he's an investor in Aduro. And John reached out to me, wanted to talk about and present some chemistry on Aduro, and I thought it was a good idea. So, John, tell me, what gave you the idea to reach out and propose it, and why you?
Well, with Aduro, and I read all the comments that show up on your videos. I read ones that show up on some of these other folks that are sharing information regarding Aduro. And there's kind of it's like when they're talking about upscaling or the hydrochemologic process, it's kind of like a nebulous idea to a lot of people, in that they don't really seem to know exactly what that entails or what that might mean. And I think it's appreciable information to anybody, especially now that we've got R2 ready to go. Just about, you're going to have people starting to work on it. And so I think just sharing a little bit of what I've learned regarding that can help kind of see where the process is going to be going here in the near future, and then when they put up R3 and so on and so forth. And so I can present a little bit of what's going on there on the mechanical side of that machine, as well as some of the basic chemistry. That we're not really going to get into the sticks too much, but enough to kind of figure what's going on from point A to point B, and then talking a little bit about how these sorts of machines and equipment, hardware, they're very prevalent in different industries. There's nothing too unique about what the hardware is that they're using. So, and I just do a lot of research. Aduro is one that I've done a ton of research on, and I think it's beneficial to have these conversations.
Okay, so let's go ahead and get started. You just take it step by step, however you prepared it.
Yeah. So the first thing to understand is monomers and polymers. And just take a quick look at a picture here. So this is a polystyrene. This is what your foam cups are made out of when you go to like the gas station. And zoom in here. This is a monostyrene, the one on the right side. And monostyrene can hook onto itself to become a polystyrene. And when you start hooking up a whole bunch of these, you can create a rather large chain. And that's what makes the very stable bonds between these carbons. And that's what makes, these plastics, durable, flexible materials generally. And then they take a really long time, of course, they just don't decompose naturally for the most part. They are very prevalent in the environment. They stick around. And we'll take a look at one more example. So this other one is going to be polyethylene terephthalate, which is PET. That's what most plastic bottles are made out of. And this is probably an example that, okay. And this one, unlike the previous one, is made up of two different monomers. And so think of a monomer like a word in a sentence. You can put different words together, and then you can have a sentence of meaningful value. And in this group, we've got the terephthalate group and the ethylene group, and they've hooked onto each other. The CH2, that's a methylate, and it can, so this N at the end, in terms of what we're seeing here, just means that we can take this chain of two monomers, and now we can repeat this, and we can create, a large chain, more plastic, and you'll have bottles and whatnot. So it's just what's going on in regards to Aduro's hydrochemologic process is that they want to take these two monomers and they want to break them apart. Or in the previous example of the polystyrene, they want to take the polystyrene, they want to make them into monostyrenes. And that takes energy. It's not exactly easy to do, but we'll get more into that. So let me go back to, actually, I'll leave that up because I don't think I need to pop into it yet. And so, and these are just two examples of plastics, but there are others. There's PET, there's polypropylene, polystyrene, and this is various plastics that you encounter when you go about, and as well as mixed feedstocks, which could be one or more of these mixed together. It could be labels, adhesives, little bits of carbohydrates that are left in like soda bottles and whatnot. And then what we want to create, like I was saying, was we want the monomers, and these can be distilled into monomer oils. And this is the product that we can then take to create. It's kind of a circular economy thing. We can make new plastics, new virgin plastics that can again be turned into all these useful products that we use all the time. I mean, you're surrounded by plastic everywhere. And so the next thing, in fact, let me swap over. So in a chemical reaction, we're just going to go over the basics of what occurs so we can take that information into what's going on with Aduro's machine. And I'll just go through this little snippet that I found. So chemical reactions involve the transformation of one or more substances into a new substance through breaking and forming of chemical bonds. In the case of hydrochemologic, it's breaking, so it's decomposition of these chemical bonds. But in the case of upcycling, it could be swapping different attachments. It could be creating new attachments. So it's kind of a different process. And then with the bitumen, that's also the decomposition. But and there's several components that go into a chemical reaction. So you've got the reactants. So in the case of Aduro, there's what the water, the solvent they put it in. I mean, it could be a reactant, but there's the feedstock, of course, and then there's the co-feed, and that's what's going to be allowing them to do a lot of what they need to be doing. But the product, as a result of chemical reaction, new substances called products are formed, and these are what we want, the monomers, the monomer oils, and sometimes gases too. So it doesn't have, you could change from one form to another. So there's going to be gases that you can extract out of these, and there's these oil liquids. And the chemical equation, we're going to get more into that later down. It'll make more sense. Or I mean the conservation of mass. But the chemical equation represents the reactants and products of a chemical reaction using chemical symbols and formulas. The reactants are written on the left-hand side of the equation, and the products are written on the right-hand side. And these two go together, and so we're going to discuss those later on. Energy changes. Chemical reactions often involve the transfer of energy from the form of heat, light, electricity. Some reactions release energy while others require energy to proceed, and that depends on the kind of bond between two atoms or two monomers in a polymer. And the reaction rate, and this is kind of an interesting one because, and as we'll get into later with the flow chemistry, you don't necessarily need a bigger machine to get more product out at the end, right? So you can have basically it flow faster. If you can create a faster chemical reaction in the system, you can get more product out at the end. You can speed up the whole thing. And so, and there's kind of a balance that you need to strike, because it can cause exponentiality in regards to some of the reactants, meaning that it's not necessarily linear trying to control this reaction. So you might need to add more of a certain catalyst or whatnot in order to produce the reaction faster than before. And so these are all aspects of a chemical reaction, and that's just changing, these bonds and creating a product, something useful out of something that you don't want. And there's a lot of ways to do it. In regards to plastic recycling, there are companies that do enzymatic solutions. So they've found some bacteria and the bacteria produce an enzyme, and the enzyme can basically eat these bonds. Primarily right now is focused on PET plastic, and this is kind of an issue with the enzymatic solution in that there's not necessarily an enzyme that can eat PET, polystyrene, polyethylene, mixed feed, and enzymes are very slow, and they can do some interesting, I don't know biology, and I don't know anything about biology, but they can do some interesting sort of selective breeding of bacteria, is a proper term for it. And then they can create a better enzyme, and then they can combine enzymes that they're aware of. And from my research, I was looking into this. So they can basically create an enzymatic powder that they can put onto PET bottles, maybe like salting it, but it's not what it looks like, I'm sure. But and then it kind of dissolves these plastics, and it takes 10 hours to do for 90%. And I was looking at some of the industrial size pilot reactors for these. And interestingly enough, it says they can do 2 tons per cycle. What is a cycle? Could be anything. A day, a week. If it was 2 tons a day, they would have said, right? But the point is, it's going to be slower. And you can't really make a continuous flow version of an enzymatic solution because it's like you're steeping it like tea, it takes time. You're going to make a sludge river or something, it's a challenging solution. And then you also need to mass produce the enzyme. You're not going to go buy the enzyme on Amazon. You need to have the infrastructure made to create the specific enzyme that's not really getting used anywhere else right now. It's this kind of small case, it comes out of labs. So then you need 2 sort of facilities involved in that process. And now pyrolysis is another one that can create these reactions in order to convert a polymer into a monomer. And it's kind of like shooting glass with a shotgun. So you don't have a ton of control because it's a lot of heat. And of course, heat is energy. And then the more heat you use, the more gas you have to deal with at the end of the process, because just like water, things will evaporate and become their gaseous form. And then these have to be condensed and turned back into a liquid. But the higher heat that you've got that gas up to, it's a different, you got to bring it back down, right? So if I have a steam, you got to turn it back. It takes energy either way. And then the other problem with pyrolysis is that, like I was saying, it's hard to control these reactions that occur in this high heat. And you've got these chains breaking apart, but there's interplay with a lot of these molecules. Oxygen can become a free radical, and among other things that are floating around in there, because these atoms all combine to they're all made of the same building blocks, is what I'm saying. Oxygen, nitrogen, hydrogen. And so these free radicals can actually create polymerization between different bits, and this adulterates the product that you get out the end. You don't have as good of a yield, and now you've got to take these bad chunks out. And the other issue is that for both of these, you have to sort. Like I was saying with the enzyme, you don't have an enzyme that can eat all of them. With pyrolysis, you can throw everything into the furnace, and then you've got a mess of what you're getting out. And labels, that turns into like ash. I mean, you're not going to make a monomer oil with ash in it. It's just adulteration of the products. And they make pyrolysis at a very large scale already. But they have to get the high quality feedstocks that are clean. And they don't have, labels and so much adhesive and whatnot. Specific kind of plastic, 1 or 2 types of plastic. And that's why you read articles that say we can only recycle 5% of the world's plastic. a number, the total number of this, it goes up every year. It's going to keep going up forever, probably. I mean, the more humans, the more plastic. So, and it's also very expensive to put these together and run because of all the heat that you have to pump into them. And you can build them profitably, but you have to build a very massive facility. So, and it takes years to pay off. And again, you're only doing a portion of what you could be doing. Now, in regards to what these chemical reactions can happen in. So when you went over to visit Aduro, you probably saw, it didn't look like this, but what they have there in the labs, and this is very common, this is the first step because it's a simple, very simple machine, is a batch reactor, which is kind of like filling up a cup, pouring something in and mixing it up, except with a chemical reaction. They also add heat and pressure to be able to produce the reaction effectively. And with pressure, the story is kind of like, you know how water boils at different temperatures depending on your elevation. So the pressure can influence the temperature at which the reaction can occur, among other things. But it's just a mixer. I mean, you put that down in there, you fill it up, you mix it, and then you extract what you want out of it. And when chemistry is done, it always typically starts with a batch reactor. And you can start to get an idea of the amount of what you put in for the feedstock or the co-feed or the reactants, and how much time it takes to produce a reaction. So you can get basic outline of a formula made for chemistry for producing a product from your inputs in the batch reactor. And batch reactors are actually used on the very, very, very large scale. In the petrochemical industry, they'll be used. In the pharmaceutical industry, they'll be used. In the food industry, they'll be used. And these have been around for like 82 years. I mean, this technology is old. And more recently, though, we're starting to see the use of flow chemistry, flow reactors more and more. And while it does the same things as a batch reactor, it's a little bit different in several key ways. And when Aduro was talking about upscaling their stuff and moving from batch chemistry to flow chemistry and all the potential benefits that we're thinking about seeing from this process.
You mean to R2, right?
Yeah, to R2, because it's the flow chemistry. So let me grab the next link. I'm going to watch a little video, short, a few clips actually to share.
So let's think about some of the benefits. So the first one here would be selectivity. So let's think about running our reactions in batch. So step back a second. Poor selectivity generally comes from loss of reaction control or some variation in our reaction conditions. And we're thinking about parameters such as temperature, mixing, addition, molar ratios, concentration, time, things that we mentioned before. So if we think about the first one, temperature, when we're running our reaction in a batch reactor, whatever that is, a round bottom flask or a jacketed reactor, or simply a small vial, when we're heating from the outside in. Our reaction will become homogeneous in temperature over time, but we generate a temperature gradient as we're heating from the outside in. As our vessels increase in size, it becomes increasingly more difficult to control our reaction temperature precisely, especially if we have very high exotherms. The larger our reactor becomes, the more difficult it is to control those functions. If we think about mixing in a batch reactor, our mixing is chaotic, it's turbulent. It's not the same in every process. We can increase mixing efficiencies by using multiple propellers. We can have baffled reactors to increase that mixing efficiency, but it's still chaotic, it's still turbulent. If we think about addition, even with controlled dropwise addition, we create concentration gradients. We have more of our reactants in one place over the next. And as we're adding more of our reagents, we can create back mixing as well, so our product can react further. So we create concentration gradients. Molar ratios come into the control of addition. Concentration isn't so much of a factor, but reaction time can be difficult to control precisely, and we can control that under flow reaction conditions. So let's think about some of these parameters in a flow sense. So let's think about mixing initially. So we can create that same turbulent, chaotic mixing under flow conditions with the use of simple static mixers. And there's an example here of a split and recombine micro reactor, a chemically etched glass reactor, where we're splitting each of those reagent additions into 3 sets, and in a 3-dimensional matrix we're splitting and recombining and splitting and recombining. And we can create very efficient mixing profiles for reactions that require high mass transfer. But under most flow chemistry experiments, we're going to be operating under laminar flow. Now you can see from the diagram here, we don't initially mix our reagents. Mixing occurs in laminar flow under diffusive mixing. So as our reagents meet, they will diffuse into one another, radial and actually. But that diffusion time is proportional to the distance squared, so it's quite quick. But the take-home message here is that it's reproducible. Every mole of our reagents that mix will see, that combine will see exactly the same mixing regime. And as we're moving our reagents on, there's no opportunity for our reagent product to react further with the addition of our reactants. There's no back mixing. So it's fast and reproducible. And that can create quite a lot of benefits. I mean, if I run an experiment with exactly the same conditions and the same concentrations today, I can reproduce that tomorrow, next week, or in a year's time, and I'll have exactly the same reaction conditions. Let's think about temperature. So flow reactors have a high surface area to volume ratio compared with their equivalent batch reactor. That better heat transfer, if I have a high surface area, I can add energy into my reaction and I can also dissipate it very effectively. That high heat transfer gives us better temperature control. If we think about, as I said earlier, heating a batch reactor, the little diagram here shows you that temperature gradient as we're increasing our reaction temperature up to the desired temperature, and even when we take that heat away, there's a temperature gradient as we cool. Because we can add energy in very effectively, reaction temperature, as soon as our reaction enters that heated environment or cooled, inversely, the same thing happens when we cool, it immediately gets to, or very, very quickly gets to the reaction temperature. And when it exits the reactor, that temperature gradient as it cools down is very fast as well. So for those that haven't seen a flow reactor, I'm just going to pause this a second so you can see this in a bit more detail. So what I have here is a simple glass-etched microreactor. So this is 1 milliliter in size. Now, the equivalent surface area to this reactor is about 80-fold smaller. If we look at a larger capillary reactor, so if we want to scale up, this would be an example of a PTFE tubing wrapped around a heat control element. So this is a larger volume. This is 16 milliliters. And if we really want to go to larger scales, we can use something like this, which is a glass flow reactor, a glass capillary, and this one's 250 milliliters. But that surface area to volume ratio is still much greater than the equivalent volume of a batch reactor. And we can control, we can flow continuously through this to create more material with the equivalent volume.
Okay, so what he's saying with the molar ratios, that would be my ratio of like plastic feedstock to co-feed. But everything else there should have made a lot of sense. So the system is inherently a lot more efficient in a flow reactor and flow chemistry because you don't have to worry about temperature gradients. So, you heat something in one area, but over here it doesn't mean it's going to be that same temperature. So there's going to be some variation, and that causes some unpredictability or instability within the reaction. In the end, it means that you're going to get a better product, ultimately, is what all of this means, and faster.
So you're saying that by using continuous process, you're going to get a better result than using batch system?
Yes, and generally it's actually a lot better. It's not just like a little upgrade. These different things mean that you're going to be able to create the same reactions with less energy. It's easier to pressurize a flow reactor system than it is to pressurize a big volume like a batch reactor. That's less energy. It's easier to heat the same volume because there's less of it again. And then the way that it mixes is also more consistent. The temperature throughout the system is more consistent. And it can potentially, and then this is a give or take, it might be able to cost less. It might be costing more, and it depends on some of the equipment that goes into it. But flow chemistry, and it's a little bit more recent to the scene, and it's picking up kind of, more processes out there in the industry within the last 2 decades. So, and it works pretty good. So the next video is the Aduro R2 walkthrough. And that's just that one on their YouTube channel where they're talking about their R2 for the hydrochemologic process.
Hi, I'm Anil Jawar, Chief Scientist at Aduro Clean Technologies. At Aduro, we are working on the development of platform technology for chemical recycling of plastic called Hydrochemologic technology. It's a simple water-based process which is capable of upcycling plastic into high-value feedstock and platform chemicals to enable circularity. It's a unique chemical conversion process which could be achieved using conventional processing equipments. This is our continuous reactor system for upcycling of plastic into high-value feedstock and platform chemicals. In tank 1, we have water and catalyst. In tank 2, we have bio-based renewable in situ reducing effluent source. They are co-fed into the reactor using a high-pressure pump. This is an auger to fill the hopper for the extruder. We can feed in polyethylene, polypropylene, polystyrene, or mixed plastic using this auger into the hopper, and they are fed into the extruder. The extruder is used like a pump here. We increase the temperature of the plastic and push the material into the reactor system. In the reactor, the plastic come in contact with our co-feed, and depending on the process conditions, which we can adjust by adjusting the temperature or pressure or even the space-time. And depending on the process condition, we get a different quality of the product. Once the reaction is complete, the material leaves the reactor system and flows into this twin separators, where we can maintain different temperature to get the desired fraction. So depending on the process condition, we can get high molecular weight waxes, or we can also get low molecular weight hydrocarbons, which are suitable for naphtha cracker feed. The non-condensable gases leaves top of the second separators and are collected. So this is, in short, our complete hydrochemologic process.
So I want to help people understand what they're looking at when he goes through that machine, and I'm going to be able to break it down really simply and then talk about some of the individual components. So this is a system diagram. Very simple, easy to show what's going on here. So in the first tank, there was water. And this is what everything's going to get mixed into. And then water, of course, is really easy to take out at the end because you can just evaporate it at a certain temperature. And then they may be doing some other stuff with the water too, but we don't know all of their chemistry. They keep it, close to the vest. The other one was the plastics. And the third one that he mentioned was NC2. Let me grab my note here. And what the NC2 was, so he said NC2 reducing salts. NC2 reducing equivalent salts are chemicals that are used in various industrial processes to reduce the amount of nitrogen oxides emitted into the atmosphere. These salts work by providing a source of nitrogen that can react with the nitrogen oxides, thereby reducing their concentration. Bio-based renewable NC2 reducing equivalent salts are a type of NC2 reducing equivalent salts, and these types derived So it's just it seems to be an emissions consideration for making it not, emit nitrogen and whatnot, but it's in the thing, so we're putting it on the graph, right? And then these come, actually these, so plastics stick over here. And these he takes into a pump. Nothing special about a pump. We're just moving stuff. The plastics are put into an auger, which is basically, it's just a mechanical machine that moves it. And the auger drops it into the hopper, and the hopper into the extruder. And I'll show you what an extruder is. It's kind of a cool little piece of equipment, and then all these components come into the reactor, just some sort of continuous flow reactor. There are different kinds of continuous flow reactors. There's coils. You can do something similar with plates, where the plates have coils in them. You can do plug flow. I think it's a coil. I'm not sure. It doesn't really matter too much at this point to get that specific, but it's a reactor nonetheless. And then they've got their co-feed, and that goes in to the reactor as well. And in the reactor, they control heat, or temperature, I guess would be a better word, but it's longer, so we'll go with heat, pressure, and space-time, which is how long it's going to be in there, basically. But it's also going to be related to the kinetics of the reaction in regards to the co-feed and different things. But you can potentially speed up or slow down a reaction. And that doesn't necessarily have to do with the speed at which the material is going through the reactor, although it often does, if that makes sense. And then these come to the separators, which, when you put products in, you want to be able to get the products out. And sometimes what's coming out is gas. Sometimes what's coming out is adulterated with other products. And they can be separated out very simply. And I'll show you, there's a very short clip for that as well. Very easy to understand. Then, of course, we get our products, which can be gas, or they can be liquid or semi-liquids. Like in the video, he shows there's one where he talks about there's some waxes they can get out of it, and some of these can be used if it's closer to a monomer oil, that can be pretty quickly used and turned around into a sellable product. If it's something like a wax or like a gas, it requires a bit more preparation, and those can be upcycled with some of their other technology in potentially the same facility. And which is really cool how the way that, I mean, they've got the upcycling and the recycling. Really, it's one thing in the finished product. They go together very well because the materials are, you're putting the same stuff that they're using. So, so the first thing, so we already talked about NC2. And look, so there's a video explaining what the extruder does.
Now let's look at the inside of an extruder to see how it works. The plastic raw material in this hopper travels by gravity to the feed throat and drops onto the rotating screw. The rotation of the screw conveys the plastic forward through the heated barrel. As the plastic is conveyed forward along the screw, the channel depth decreases, forcing the plastic through a smaller area. The combination of compression and screw rotation causes friction, which generates heat. This is called shear heating. This heat, along with the heat from the barrel heating system, melts the plastic. By the time the plastic is conveyed to the end of the screw, It should be well mixed and at a proper temperature and pressure needed by the die. The plastic is called a melt at this stage.
It depends on the heat and pressure that they put into this machine and the extruder. And then I can go into the rest of the system from there. So not a terribly complicated machine, but as you know, they got to have it. So, and then the next machine we're going to look at is, well, actually, no, we're taking a look at the separators now.
Different hydrocarbons boil at different temperatures. During the boiling process, each type vaporizes at a precise point, then gets separately funneled into a container and collected as a liquid as it cools.
So we're not necessarily talking about crude oil in this example. I mean, we're not, but the same is true. Different substances will boil at different points, and the same is condensed at different points. But you take these and you can separate them out, basically gas and liquids, or liquids from gases, or if you've got two things in the same volume or solution, you can take them apart. And there are other ways to do that too. I think that's what's going on here, is they're just distilling it. But there are other methods, and none of them are terribly difficult to understand. I mean, it's pretty simple compared to what else is going on in this system. So, and that's what you're looking at in that Aduro video, is just this. They've got all these pipes on there now, and they got some pressure gauges and monitoring equipment, which are like electronics, and you can kind of peer into the live system with like a UV sensor. It can detect certain molecules and whatnot. And that's another benefit of a flow reactor system, is that you can do all of this in real time, and you can modify the reaction in real time. So it makes it a much more iterative process than a batch reactor when it comes to working. And a lot of what's going on here now with R2 is that they're working on upscaling the reaction from the batch reactors in their lab. And then when they get to some point where they've got it all written down, and what's most efficient, the best amount of time, space time to have it running at, they can strike a balance to figure out how we can get a product at the end with the least amount of needed energy, the least amount of needed time, maybe the least amount of needed co-feed and whatnot. And it's a lot of experimenting. It's a lot of testing things, running them down, testing things, running them down. And to help explain kind of what they do in regards to their chemical equation, got one more tab to share. So I'll scroll down here in this paper. What I want to look at is this. So in any reaction, what you're going to have is you're going to have your inputs, you're going to have your outputs. The mass of your inputs and the mass of your outputs, irregardless of what bucket they fall in, you can have more than one input and output. And you can have outputs that aren't really things that you need. But the mass of what's going in is going to come out one way or another. You're going to know where it ends up at. And so when you have a reaction in a batch scale, you've got how much mass I want to have here, how much output I want to have here. I know that I get an accumulation of waste over here that I can get rid of, but I've got it measured out where all the mass is going. And when you convert that to a larger scale, on paper, it's a linear equation. So you can take the inputs and you multiply all of them, and then that means all your outputs are going to be multiplied by the same number. But in reality, that's not actually what happens, because the size of the machine can affect the variables of the reaction. And so what occurs initially is that you're going to have your outputs are not going to be what you desire. So you're going to have some of the outputs, like whatever the waste value is, or maybe you're getting too much or too little of a certain end product, or it's adulterated or whatnot. And so what they do is they work and they change some of these values, and they work and they change some of these values, and they can see that they're getting closer when they see that their outputs are getting closer to the desired values. Once they get to, and the reason why you go from like a small scale in a lab to something like an R2, which can fill a room, and then something bigger, and then something bigger, is that it becomes more and more complicated as you go along. And when they get toward the industrial scale reactors, it's not going to be just one chemical reactor. They're going to be able to put several in serial configuration, so they can deal with multiple different types of plastics. But that sort of system that we drew in the previous on the whiteboard, I mean, it starts to look pretty complicated even on the whiteboard. But you need to have each one of these components, and they can test in the same R2 multiple different components. They just configure it differently. And then they can have all these different equations that they put together. And that's what they use when they go up to a larger scale and they start combining multiple pieces of this machine together. And so it's not necessarily a matter of asking. There are people that talk about, what are the concerns of upscaling? What are issues that might arise? It's not a hardware issue. All the hardware you saw in the video, all the hardware that they're going to be able to use, I mean, a lot of this stuff is already produced at a mass industrial scale. Extruders are used in the food industry. I mean, very, very big extruders. Of course, extruders are often used for actually making plastics, but they're massive. And I mean, tanks, I mean, it's just a volume. It's a steel drum, None of this stuff is terribly complicated machinery. None of this stuff is like super unique. They're just taking existing technology, they're making a new configuration of it, putting it together, and now they can do their chemistry in their configuration. So of course,
so when they're saying they're not too concerned about scaling it because it's all in the chemistry. So that's pretty much what you're saying.
Yes. It's all in the chemistry, and what that means is man hours and paying, qualified professionals that are dealing with this day after day. It really just boils down to, of course, money. They need money to get from one process to the next process, and it's something good to see with Aduro in that. I mean, they've got the partnership with Shell. They received grant from the Canadian institution. They've had some third-party verification of their chemistry. What the question is, does their chemistry work? Will it work when they scale it up? And scaling up of chemistry, I mean, this is done all the time. Every large industrial process that you see out there, pharmaceutical, petrochemical, all of these, it's the same process, is what I'm saying. And that they have to scale them up and they go from one size to the other. It's a well-trodden path. But each time you're going to do it with a unique chemistry, there's going to be unique complications that might arise. And I can't speak to, all of that, but hopefully this illustrates kind of that process and is helpful to people.
Do you live in the United States?
Yeah, I live in Utah.
Okay. So have you considered visiting Aduro?
Yes, I'm going to go. I was planning early next year, February or January is when I heard. It might be sooner. They're going to be opening it up to having some investors come and look, and I want to go and investigate that.
So far, by listening to Anil's presentations, what is your reaction to his knowledge about chemistry?
He's very extensive. Yeah, I mean, the guy knows a lot. And he was doing this a long time. I mean, he's got, his PhDs and whatnot. I mean, he knows what he's doing. And he's a chief scientist, right? I mean, he's the #1 guy, and he's leading the teams. This is the sort of thing that he's going to be concentrating on, is not only just the configurations of the machines, and there's some business to do with the procedures. He's got to, write procedures, the safety procedures and whatnot, and instructions and as to how to operate the configuration of the machines. But I mean, the guy knows a whole lot more than I do, that's for sure.
Yeah. Okay. Well, thanks, John, for sharing your knowledge with us here and trying to break it down in basic terms.
You're very welcome. My pleasure.